inverse trigonometric functions, and we're going to create them by inverting the original trig functions, but we will have to make some restrictions on. Before we get started talking about inverse trigonometric functions, we really need to review about what an inverse of a function actually is. And if you recall, if we look at the left part of this diagram here, a function is like a machine. It takes input, in this case apples, it does something to the input, we call that the function's rule, and it creates an output, in this case limits. Some sort of operation takes an input and turns it into an output. The inverse of a function, if you recall, takes the output of a function, does an inverse operation to it, and turns the output into the original input. So in this case, the right-hand part of this diagram, the lemons that are the output from the function become the input to the inverse function, which then returns apples, which was the original input of the function. So inverse functions are a way to kind of reverse the function's process. They're very, very useful. One common use of inverse functions that you probably use once in a while is called reverse phone number lookup. You can use, of course, the phone book or the internet to find someone's phone number. So the function is, in this case, you input their name, the output is their phone number. Well, if you have a phone number and you want to figure out who it was that's calling, that's called reverse phone number lookup, and that's an inverse function. It takes the output of a person's phone number and returns the original input, which was the person's name. Two functions that are actually not trigonometric functions, but are traditionally taught as the first inverse functions people learned, and that is f of x equals x squared, and f inverse of x equals the square root of x. But something's not quite right with this pair, if you recall from your study of inverse functions. What's wrong with it? And congratulations if you figured out that the top function, the x squared function, really doesn't have an inverse because it's not a one-to-one function. Every input isn't paired with exactly one output. Therefore, it doesn't pass the horizontal line test. If you take a look at it, it fails just about everywhere. Note that the 2 points in the graph and also on the line y equals 4, so f of 2 is equal to 4 and f of negative 2 equals 4. So how in the world can we create an inverse function out of y equals x squared? Because clearly, y equals x squared by itself does not have an inverse. So how do we arrange for it to have an inverse? Well, we do it by restricting the domain. We'll consider only the part of the graph where x is greater than or equal to 0. If we limit ourselves to the right-hand portion of the graph, y equals x squared does have an inverse, and it is the square root of x. It passes the horizontal line test, and it passes the graphical test of what an inverse is supposed to look like, and that is it's supposed to be reflected across the line y equals x. So by restricting the domain of the x squared function to all x is greater than or equal to 0, we create an inverse function for it, where otherwise it would not have. We have to do that to trigonometric functions to be able to create inverse functions for them. Let's take a look at the sine function. Clearly, you can see virtually everywhere on the sine function, it's going to fail the horizontal line test. The horizontal line is going to touch the sine function in much more than just the two places you see, because as we know, the sine function continues indefinitely from left to right. So it's going to touch it an infinite number of times. How can we come up with a valid inverse function? Well, we can do it by restricting the domain of the sine function. Well, how would you do it? We've talked about that in class. You take a look at a piece of the sine function where it covers pretty much all the values. And a really good place to look at is from negative pi over 2 to pi over 2. If we look at those angles, the sine function goes through its entire range of numbers from negative 1 to 1. So we're going to build the inverse function for the sine, which we can call arc sine or sine minus 1, because it's going to pick up all the outputs of the sine function from negative 1 to 1. And it's only going to pick them up once. This little section is going to pass the horizontal line test. So this includes the origin and angles in quadrant 4 and quadrant 1. Quadrant 4 angles are going to generate negative ratios for sine. Quadrant 1 angles are going to generate positive ratios for sine. So let's zoom in and look at some of the key points. You recall the values of the sine function from 0 to pi over 2. 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. And then over in quadrant 4, the same thing in reverse. It's going from negative 1 to 0. So it passes through all those values, including those critical red values shown here. As you did with inverses in the beginning, you swap the inputs and the outputs. You can start to get a picture of what an inverse sine function looks like. For example, if we take the point negative pi over 2, negative 1, and we switch the inputs and the outputs, which is what inverse functions do, you're going to plot the point -1, -pi/2, and so on. And so notice, domain for sine is -pi/2 to pi/2, so that becomes the range of the arc sine or inverse sine function. Now, you're going to see two ways to write inverse sine. One is the word arc sine, and the other is sine -1. Both are widely used, and you need to learn both of them. So the key point here is that we're swapping the inputs and outputs, x and sine x, to create that inverse function. Range and domain are swapped out here. And here's what the graphs look like. The graph in red is the sine function. The graph in blue is the arc sine function. And again, it is passing that, not only does the original function pass the horizontal line test, but the inverse is a reflection about the line y equals x. So you can see the original function, the red sine, and the new arc sine function are reflections of each other about the line y equals x. And notice, if you look at each point on there, it's getting reflected across that axis, like a good inverse function is supposed to do. Very important point down here, you're going to see the inverse listed as both arc sine of x and sine -1 of x. Let's look at a couple of examples. For example, the sine of pi/2, that quadrantal angle, you know is equal to 1. So therefore, the arc sine of 1, or the sine -1 of 1, the sine inverse of 1, is equal to pi/2. We've switched the inputs and the outputs. Again, inverse functions are going to answer the question, what value gives me a sine of this? The sine of pi/3, you know, is the square root of 3/2. So the arc sine, or the inverse sine, square root of 3/2 is equal to pi/3. Now, most of the time we are going to use radians for this unless your problem specifies degrees. Key point for inverse functions, the original functions, the input is the angle, the output is a ratio in a triangle. For an inverse trig function, the input is the ratio and the output, the answer, is the angle. So in situations where we want to find what the angle is, that's when we're going to use inverse functions. We can generate inverse trig functions for cosine as well. Here's the function for y equals cosine of x. You can see again, it's not going to pass the horizontal line test. What do you think a good domain for that would be? Good job if you realize that the sine restriction that we used from -pi/2 to pi/2 isn't going to work, because that's just going to get that positive portion of the cosine graph. Remember that the cosine graph is even, whereas the sine graph is odd. It makes sense that their inverse functions are going to be different. And the normal convention for inverse cosine is to use from 0 to pi, because at 0, the cosine is equal to 1. At pi, the cosine is equal to -1. And from 0 to pi, it goes through all the values from 1 to -1. So the domain for the cosine, in this case, is 0 to pi. That becomes the range of the inverse cosine function. Since the range for the cosine function goes from -1 to 1, that becomes the domain of the inverse function. And this is what arc cosine looks like. Notice on the input axis, we have values of cosine, and on the output we actually have angles, and it only goes from 0 to pi. So its output is from 0 to pi, its range, its input is from -1 to 1. Other trig functions have to have similar restrictions because they repeat themselves as well. Tangent, because it's odd like the sine function, it makes sense that it's going to be fairly similar in its inverse function's domain. The domain of the tangent function that generates the arc tangent or the inverse tangent is from -pi/2 to pi/2, just like the sine. So there's the tangent function. Remember, these vertical red lines are asymptotes because the tangent function doesn't have a value. It's undefined at odd multiples of pi/2. Here's what arctangent, or inverse tangent, looks like. So we flipped the inputs and the outputs, and the inputs actually now become all real numbers because, as you recall, that's the output of the tangent function. It goes from -infinity to +infinity in its outputs. That becomes the inputs of the arctangent function. Arctangent, its inputs can go from -infinity to +infinity. Because the input of the tangent function is restricted from -pi/2 to pi/2, the output of the arctangent function is similarly restricted from -pi/2 to pi/2. So again, the domain of the tangent function is shown down here, and it's flipped around to give us the domain and range of the arctangent function. And here's a summary of everything we've talked about in terms of the domain and range of the arc sine, arc cosine, and arc